Today's lesson, section 1.5, is titled Equations for Uniformly Accelerated Motion. And in this lesson, we will be coming up with 5 unique equations that will allow us to solve problems dealing with motion in physics. And we're going to do this by drawing graphs, analyzing these graphs, and using the skills we've collected in math. So here we have a graph that should be familiar to you. It's a velocity time graph, and it shows an object's velocity as it's increasing from v1 to v2 over an elapsed period of time. By the fact that this is a straight line, we assume that the object is accelerating positively. So its velocity is changing from v1 to v2, and we want to be able to determine where the average velocity would lie on this graph. Well, if it starts off down here and ends up over here, its average value for its velocity should probably be right in the middle of these two sections. And we're going to call this point average velocity. We could actually calculate the value of the average velocity just like we calculate the average of anything in math. We say that the average velocity in this case can be determined by adding v1 plus v2 and dividing it by the number of identities here, and in this case it's 2, and that would give us the average velocity. So to recall, if we had a velocity time graph, we could find the area under this curve, and the area under this curve would give us the displacement during that interval of time. So this area gives us the displacement. It would be as simple as us finding the area of this shape. And this shape looks like a triangle stacked on top of a rectangle, but I want us to look at it in a different way. I want us to find the midpoint of this line right here, and I want you to draw an imaginary line straight across it. If we took an imaginary pair of scissors and cut this graph along this line straight through that red dot, we could take this tiny triangle up top, and if you hung on to it and spinned it around, it could actually fit in this space right here. If you did so, what you would create is a regular rectangle. A rectangle whose height would be the average velocity, that point right in the middle between v1 and v2, and whose base would be delta t. So we could come up with an equation for the displacement, and the equation would look like this. Delta d is equal to base times height. In this case, delta d is equal to delta t times average velocity. Now in the previous slide, we came up with an equation for average velocity. So we can actually rewrite this as delta d is equal to delta t times v1 plus v2 over 2. And in fact, this is the first equation. And we normally rewrite it like this. So this is equation 1. The first of 5 equations that we will be deriving. Recall the equation for acceleration. Acceleration is equal to delta v over delta t. Well, we want to rearrange this equation so that we can have an equation that will allow us to find the final velocity. This is a common question that arises, especially when studying physics. Determine the final velocity of the object. So if an object's accelerating uniformly for a given amount of time, what will its final velocity be? So let's rearrange this equation into a more practical expression. The first thing that we can do is rewrite this as acceleration is equal to v2 minus v1 divided by delta t. So what we want to do is get v2 by itself. So we're going to start off by getting rid of this delta t. Multiplying both sides by delta t will give us a delta t is equal to v2 minus v1. Our next step would be to get rid of this v1. So what we're going to do is take this v1, bring it over the equal sign. When we do, its sign will change from negative v1 to positive v1. If we rewrite this, now bear with me as I write it in this format, a more conventional format, one that you will see in the textbook. v2 is equal to v1 plus a delta t. So the v1 has become positive, but I've placed it in front of the a delta t. And again, that's just because of convention. You generally see all velocity terms before acceleration terms. So this, my friends, is equation number 2. For our third equation, we're going to take a look at the same graph. It's a velocity time graph. So in order to do the displacement from a velocity time graph, again we will be finding the area under the curve. But this time, we're going to use the simple shapes that we can break this up into. So we're going to break this shape into a triangle and a rectangle. We'll call the rectangle area A and the triangle area B. So the equation for displacement would be area A plus area B. Area A is a rectangle whose formula is BH, and area B is a triangle whose formula is BH over 2. So we can fill in these values. The base of this rectangle is delta t, and its height, this rectangle goes all the way up to v1. So it's going to be delta t v1. Let's do the same for the triangle. The base of the triangle will be the same as the rectangle, and it's delta t. Now the tricky part is determining what this value is here for the height of the triangle. Now the triangle doesn't start at the bottom or at the x-axis. It starts at v1 and goes to v2. So the value for the height of this triangle would be v2 minus v1. And we can write v2 minus v1 as delta v, v2 minus v1. Divide this by 2, and that is our equation for a triangle. In order to solve this equation, as it stands right now, you would need delta t, you would need v1, and you would need, in order to find delta v, you would need both v2 and v1. But I want to replace this. And we're going to replace it using the equation acceleration is equal to delta v over delta t. We can rearrange this, and if we do, and I'll write this off to the side, delta v is equal to a times delta t. So as you can see, what we've done is we've placed a delta t in where we had delta v. And the reason why we're doing this is because now, with the variables that are present, you can solve for displacement given v1, delta t, and acceleration. This equation doesn't require that you already have the information about v2. If you had information about v2, you could have simply used equation 1 that we solved for earlier. So this gives us an alternative. Now this is not written in proper mathematical convention. For example, we have a delta t here multiplied by a delta t here. If you have delta t times delta t, you can simplify it by saying delta t squared. So the way this equation is properly written is like this. Delta d is equal to v1 t plus 1/2 a delta t squared. And what they've done is they've taken this 2 and pulled it out front, so now we have 1/2 a delta t squared. And this is equation 3. Equations 4 and equations 5, you're not responsible to know how to derive them. And they look like this. Equation 4 is written as v2 squared is equal to v1 squared plus 2a delta d. This equation is useful and unique for one simple reason. This equation can allow us to calculate any of the variables without knowing time. So it presents a useful tool to us as it provides an opportunity for us to perform calculations without the use of time. Equation number 5 and the final equation looks like this. This equation is similar to equation number 3. Instead of v1, we can use v2. And instead of adding 1/2 a delta t squared, we're actually subtracting it. These 5 equations, you'll be using them throughout the remainder of this unit. These 5 equations, you're not asked to memorize them. We'll provide them to you in a formula sheet for every quiz, test, or final exam. Your job is to be able to know when to use them and how to use them properly.